Thank you, Andrew. So I'm amazed by the remarkable things that bacteria can do. Bacteria, as you know, are very small. In fact, these have been blown up considerably. Most bacteria that we work with are about 500 times smaller than the period at the end of a sentence on a printed page. Of course, you knew that. But what you may not know is that most bacteria are actually not harmful. In fact, many are very beneficial and maybe even essential for how we work. They're actually smart. They can communicate with one another using small molecules as their language, so they're social networkers just like you are. They can recognize their situation, and if they like it, they can stay there. If they see a better neighborhood, they can move towards it, or if their situation is getting worse, they can move away from it. And of course, they can replicate themselves every 20 minutes or so. So these are pretty complicated behaviors that we're interested in understanding and possibly taking advantage of. So how do bacteria know how to do this? Well, it turns out they're programmed to do this in their genome. And there it is. So the E. coli genome is actually just a single circular piece of DNA consisting of chemicals, A's, T's, G's, and C's. There's about 4.6 million of those. Okay? So is that a big number or a small number? Well, remember that genomes are just chemical repositories of information. It's just a way that the cell stores information. So how much information is it? Well, it turns out you can fit all of it on one of these. Whether you could read it is a different question. And of course, I teach young people for a living, so they don't even remember what these are. So you have to put this into perspective for them. So the larger point is it doesn't take a lot of information to program what are really complicated behaviors. So molecular biologists have taught us over the past 60 years or so how to go in and essentially cutting and pasting, we can change the memory of these cells and get them to do some new stuff. And we've gotten very good at this. And of course, many of you are probably aware of Dr. Craig Venter and his colleagues recently was able to actually chemically synthesize a genome, along with the help of another organism, and essentially transplant that genome into a new organism and have it boot up, much in the same way that you would install a new operating system on your computer. And although this is very expensive, it works, and I think this will become much more common. But so what? Okay, so let's say you could put a new genome in a cell. You need to have a way of interacting with it, much in the way, if you have a computer, you need an input device and an output device. And I'm interested in programming cells, so we need to have a way to talk to them, to communicate with them. So what we want to use is our small molecules as a way to tell cells what to do and when to do it. Okay? So which small molecules are we interested in? Here's one that we've been working on for a little while, and it's known as Atrazine. We spray a lot of this in the US. In fact, they spray about 76 million pounds every year on farm fields in the US. Not so much in Europe because they've actually banned its use. 76 million is a big number, and just to put that into perspective, I'm an airplane geek. This is a 747-400. It weighs about 400,000 pounds empty. We spray the equivalent of 186 of these by mass across the US. And as you can see from this map, this is where we spray atrazine. It's sprayed largely in the Midwest to eliminate weeds from mostly corn crops. Okay? And I grew up in the Midwest, so I'm a little bit sensitive to this. So, of course, whether we intend to or not, if you spray that much of something anywhere, it is going to get in places you don't want it to. So here's an article from the Times last year showing that. And as you can see, atrazine is actually now a fairly common contaminant in groundwater in the Midwest. So bacteria actually do a lot of amazing things, as I told you. And one of the things that they've evolved to do, at least some of them, is destroy atrazine. And this is a remarkable evolution story because atrazine is a completely synthetic chemical. It didn't exist in the environment until it was introduced a little under 60 years ago. So we want to be able to take bacteria and essentially program them to actively seek out atrazine and destroy it while ignoring things that they might otherwise be attracted to. So it turns out E. coli actually already know how to do this. They can chase molecules they like, and if they are moving in a direction where the concentration of the molecule is increasing, they'll tend to keep going in that direction, whereas if the concentration is decreasing, they'll tend to turn around and try something else. So bacteria, thank you. I was going to wear a gorilla suit, but that works too. And it turns out, of course, like all these processes, you need to have the correct genes turned on and off. And here, the E. coli on the left are the ones you've seen. They're natural. The ones on the right are missing a single gene, and they look kind of sad. So obviously, what we want to be able to do is flip that gene back on so that the cells actually seek out atrazine. And my lab has been developing ways to turn genes on and off using small molecules. And the way that we do that is using something known as a riboswitch, which is made of RNA, which is a chemical cousin of DNA. And a riboswitch can flip genes on and off using small molecules, in this case, atrazine. So what we've actually been able to do, can we go, there we go. We've actually programmed cells so that in the absence of atrazine, they don't move. And when atrazine is present, they will actually seek it out and migrate towards higher concentrations of atrazine. And by adding additional genes from cells that have evolved the ability to break that down, we've actually endowed these cells with the ability to act smart. They can actually seek out atrazine and start breaking it down. So I'll just conclude by maybe making it, rather than making a strong statement, I'll actually just ask the question of you, what's next? Just as we can program computers to do lots of wonderful things, and in some cases some not so wonderful things, we'd like to think about what sorts of operations should we be programming organisms to do, and maybe what are some of the things that we shouldn't be doing. So I'll just thank you all and thank the folks that did it. If you want to visit us on the web, you can do so there. Thank you for your attention.